Hello everyone. The topic that we are going to cover today is semiconductors. So as we all know, semiconductors are a class of materials that we know right from our schooling, right? And what are semiconductors? So semiconductors are the class of materials which have their conductivity value that is lying somewhere between the conductivity values of insulators and conductors. And if we want to list out the properties of semiconductors, then we can say that they are the materials which have the partial conduction, and then number two, at T is equal to 0 Kelvin, they will be behaving as a perfect insulator. And as we are going to increase the temperature value, then the semiconducting material will start to behave as a conducting material. So these are also some of the basic properties of semiconducting materials. And when it comes to types of semiconductors, there are different criteria based on which we can classify the semiconductors. Number one, based on the composition, you can classify it as elemental and compound semiconductors. In case if you are going to classify the semiconductors based on impurities, then we could see that there are two main types are there. One is intrinsic semiconductor and the other one is extrinsic semiconductor, right? So these are the two broad categories of the classes of semiconductors based on the impurity atoms that have been introduced into the system. And what about intrinsic semiconductors? Just to give you an overall broad idea about it, intrinsic semiconductors are the pure form of semiconductors, whereas as the name itself implies, extrinsic semiconductors are the materials which have some presence of external impurities in it. And in this session, we are going to cover both this intrinsic semiconductor and the extrinsic semiconductor and its subtypes in detail. Okay, and what are the points that we are going to cover in this session is we are basically going to discuss the basic points related to both these classes of semiconductors and also how these two semiconductors will behave at T is equal to 0 Kelvin and what happens eventually when we are going to increase the value of temperature. That's exactly what we are going to discuss in this session. So let's first start from the discussion on intrinsic semiconductors, right? Right. So as I have been mentioning, intrinsic semiconductors are the pure form of semiconductors. It is the pure form. And also, group 4 elements comes under this intrinsic semiconductor category. When you say group 4 elements, some of the basic examples are silicon and then germanium. These are the basic examples. And we also know that when you say group 4 elements, almost all the group 4 elements will be having the tetravalent nature. So tetravalent atoms or tetravalent elements they are. So what's the meaning when you say a system or an atom to be tetravalent in nature? It means that simply they are going to possess 4 valence electron for it, right? So these are the most important key points that we must know related to the intrinsic semiconductors. So first thing, it is the purest form of semiconductor without any presence of impurities. Number two, group 4 elements comes under the intrinsic semiconductor example, and group 4 elements like silicon, germanium, they are trivalent in, tetravalent in nature. Sorry. And let's see how this intrinsic semiconductor will behave at T is equal to 0 Kelvin and what happens when we are going to increase the value of temperature. First thing, let's discuss T is equal to 0 Kelvin, right? And let's suppose a network of silicon atom. We are going to suppose an intrinsic silicon semiconductor. So obviously what we are going to have inside the atom, inside the material, a network of silicon atom we will be having. So let me represent that network of silicon atom in this fashion, where we are going to represent the 4 valence electron that is belonging to each and every silicon atom by these 4 dots. All these 4 dots are representing the valence electron possessed by each and every silicon atom. And what these free electrons are encased in? These free electrons are encased in the formation of the covalent bond by mutually sharing the electrons between each other. Okay, so we will be having a huge network of silicon atom where each and every silicon atom will be sharing their 4 valence electron mutually with each other, and thereby they are going to form covalent bond between them. And you can clearly see from this representation there is no free electrons that is available, right? And when there is no free electron, obviously the system is not going to be conducting in nature. And that's the reason why we claim that at T is equal to 0 Kelvin, intrinsic semiconductor will be behaving as an insulator material, insulating material, since there is no free electrons that are available. Now, if you want to convert this semiconductor into a conducting material, then the only option that is left with us is you have to make use of the temperature. If you are going to increase the value of temperature, let's suppose that we are going to increase the value of temperature. By increasing the value of temperature, some events are going to follow, and eventually some changes is going to happen in this material. What is that changes? We will explore that in detail in a short while. Before that, let us draw the corresponding energy level diagram for this intrinsic semiconductor at T is equal to 0 Kelvin condition. You could clearly see that whenever we talk of semiconducting material, we always talk about the energy bands. So what are the 2 energy bands that we always talk about? One is valence band with the topmost energy value of EV, and the other one is conduction band with the bottommost energy value of EC. Now, all these electrons, free electrons, which are all these valence electrons, which are completely engaged in the formation of covalent bond, they all will be residing at the valence band. Okay, so whatever electrons that are encased in the covalent bond formation, they all will be residing at the valence band. And you could clearly see that there is no presence of electron in the conduction band, which means there are no free electrons, and thereby at this scenario the material is going to behave as a perfectly insulating material, right? So this is the condition when T is equal to 0 Kelvin. Right. Now what happened when we are going to increase the value of the temperature, which means T is not equal to 0, but it is going to be greater than 0 Kelvin. Okay. And we clearly know that the energy difference between the conduction band and the valence band is what referred as band gap energy. So let's suppose that by increasing this temperature value, the electron in the valence band will be gaining energy now, and which means according to this network, some of the electrons which are encased in the covalent bond formation, they will be experiencing increase in their energy. And let's suppose that this particular electron is now gaining an energy, and as this electron gains energy, what happens is this covalent bond will get broken. And when this covalent bond gets broken, it simply means that this electron is set out as an free electron. Now it is becoming free. And when an electron becomes free, correspondingly, a hole is created on the initial electron's place. Okay. So what has been created now? A hole has been created. And while the hole is created, what is happening? Actually, a free electron is being introduced into the system because of the influence of the temperature. Now, let's associate this with the energy level diagram. And as we discussed just now, one of the electron is now gaining the energy and it is moving to the conduction band. Let's say this is the electron that is now gaining the energy because of the influence of temperature, and it is moving up to the conduction band. When this electron moves to the conduction band, what is correspondingly created on the valence band? A hole is created on the valence band. Again, if this electron gains energy and moves to the conduction band, then you have an additional presence of the electron in the conduction band, and Accordingly, you also have the creation of a hole in the valence band. If this electron is gaining energy, then it is going to move to the conduction band, and thereby a hole has been created in the valence band. Okay. So as long as we are going to increase the value of temperature, under the influence of the temperature factor, all these electrons which were previously encased in the covalent bond formation will be breaking the covalent bond, and they will be set as free electrons. And when they become free, it simply means that from the valence band they are making the transition to the conduction band. Right? Now, if you say the concentration of free electrons in the conduction band as small n, and the concentration of holes in the valence band as small p, then we could see that for the intrinsic semiconductor at a given temperature, we can give a relation small n is equal to small p. That is, the number of electrons, free electrons in the conduction band will be exactly equal to what? Will be exactly equal to the number of holes in the valence band. Why? If at all an electron is present in the conduction band, it has to come from the valence band by breaking the covalent bond formation, and thereby one hole will be present in the valence band. அப்போ இங்கே how many electrons are present in conduction band, correspondingly that many amount of holes are going to be present in the valence band. Okay, and this is why we claim that the intrinsic semiconductors will behave as insulating under the condition T is equal to 0 Kelvin, whereas when you increase the temperature, it is eventually turning out into the conducting material. So this is the small mechanism that actually happens under the influence of temperature in case of the intrinsic semiconductors. Now, with this understanding, let's get into the extrinsic semiconductor part. Right. So as we already mentioned, what is extrinsic semiconductor? Basically, extrinsic semiconductors are the ones with impurities, right? So they are the combination of an intrinsic semiconductor which is added with, or to be more technically defining that, which is doped with some impurity atoms. We clearly know what is impurity atom. Something which is completely alien to the parent network of atoms, that you can claim it as the impurity atom, right? So if I am going to add the impurity atom into the already existing intrinsic semiconductor, then such a system we are going to call it as the extrinsic semiconductors, right? Now, the next question that naturally follows is, why should we add this impurity atom into the intrinsic semiconductor? Why not use the intrinsic semiconductor in its pure form? Why should we contaminate it? It's not entirely right in the right sense, but still we are adding some impurities. And that in that context, I'm just telling that addition of impurity atom is being done into the intrinsic semiconductor, and there should be a purpose behind it. And the main purpose is, the reason is, if you take the intrinsic semiconductor, it has been observed that their electrical conductivity value is much smaller. Okay, but when it comes to practical application, we will be in need of semiconducting materials which should be able to exhibit the higher value of electrical conductivity for the practical purpose. On that note, intrinsic semiconductors are having a small minor setback, that they are only able to exhibit the lower value of electrical conductivity. Why? That's the reason behind it. Because when it comes to intrinsic semiconductor, the concentration of charge carriers, when you say charge carriers in semiconducting material, we simply mean by the electrons and then holes. Okay, so electrons and holes, இதனுடைய concentration வந்து it is found to be much smaller. The concentration of electron and hole, as we mentioned, small n and then small p, their value are found to be much smaller. So obviously, in case of semiconducting material, if the electrical conduction is mainly due to what? Mainly due to the flow of charge carriers. And if the electrical conduction itself is due to the flow of charge carriers, then the electrical conductivity will be obviously very smaller, as the intrinsic semiconductor found to have the smaller concentration of the charge carriers. Now, the main purpose of adding this impurity atom into the intrinsic semiconductor is, the first and foremost reason is, the immediate impact is going to be, we are in the process of increasing the concentration of the charge carriers. So once you increase the concentration of charge carriers, obviously it is going to have an indirect influence on the electrical conductivity property of the material, right? Now, once we add the impurity atom into the already existing intrinsic semiconductor, what will be formed? Obviously, the extrinsic semiconductor will be formed. Now, based on what type of impurity atom we are introducing into the intrinsic semiconductor, extrinsic semiconductors are classified as two types, and they are N type and then P type. In case if I am going to add the pentavalent impurity atom, then the type of semiconductor is referred as N-type semiconductor. And in case if you are going to add the trivalent impurity atoms into the intrinsic semiconductor, the semiconductor in this case will be referred as the P-type semiconducting material. Okay. Now, let's discuss the N-type semiconductor and the P-type semiconductor individually to explore how this N-type as well as P-type semiconductor will behave at T is equal to 0 Kelvin, and what happens when we increase the value of temperature. Okay. So, as I mentioned, the first semiconductor that we are going to discuss now is N-type semiconductor. Now, I clearly mentioned that N-type semiconductor is formed by adding pentavalent impurity atom into the intrinsic semiconductor. So basically, it is a combination of intrinsic semiconductor which is doped with this pentavalent impurity atom. And if when you say pentavalent impurity atom, you can name phosphorus as an example for it. So what is pentavalent impurity atom? Those impurity atoms which have 5 valence electron in it, they will be claimed as the pentavalent impurity atom. Now, what happened when we introduce this pentavalent impurity atom into the already existing intrinsic semiconductor? It is going to result in the increase in the concentration of one of the charge carrier, and here particularly it is going to result in the increase in the concentration of free electrons. Since the value of free electron is increasing, since the concentration of free electron is increasing, this type of semiconductors are referred as the N-type semiconductors. Negatively charged electron concentration is drastically increased with the help of the impurity atom added into the system, and thereby these semiconductors are referred as the N-type semiconductors. And the impurity atoms, namely the pentavalent impurity atom which we are adding into the intrinsic semiconductors, in this case are referred as donor impurity atom. There is a reason behind why it is referred as donor impurity atoms, and because of the introduction of this donor impurity atom, we have an introduction of a new energy level which we call it as the donor energy level. Okay. So these are the basic points that we must know related to the N-type semiconductor, where we will be doping the pentavalent impurity atom into the intrinsic semiconductor, and because of this addition, it is going to lead to the increase in the free electron concentration. Obviously, when you have the increase in the free electron concentration, that will be reflected in the increase in the electrical conductivity value. So, job is done. and the impurity atom which is added in the intrinsic semiconductor, in this case of n-type semiconductors, are referred as donor impurity atom, and the new energy level which gets introduced into the system due to the addition of the donor impurity atom are referred as donor energy level. Right. Now, as I was mentioning, let's explore how this n-type semiconducting material will behave at T is equal to 0 Kelvin and what happens when you increase the value of temperature. Okay. So, first let us represent T is equal to 0 Kelvin. Right. And when T is equal to 0 Kelvin, as I mentioned, let's say you are having a network of the intrinsic semiconductor. So, what we have? We are going to have the 4 valence electron belonging to each and every silicon atom. Okay. And all these 4 valence electron will be mutually involved in the formation of covalent bond formation, and thereby, as you know, there is no free electrons that are available. So, you are going to have the network of silicon atom as such like this. Now, what we are doing? We are going to add the pentavalent impurity atom into it. So, pentavalent impurity atom like phosphorus, it will be having 5 valence electron, number 1, number 2, number 3, number 4 and then number 5. Right. Now, when you add this phosphorus atom into the already existing silicon network, then immediately what happens is, the consequence is one of the silicon atom will be replaced by this phosphorus atom. Right. Now, out of 5 valence electron possessed by this phosphorus atom, 4 valence electron will be involved in the formation of the covalent bond formation with the surrounding silicon atom. So, out of 5 valence electron, 4 valence electrons are involved in the covalent bond formation. Right. Now, what about the 5th one? So, the 5th valence electron belonging to this phosphorus atom is now newly introduced into the system as the free electron. Initially, there is no free electron when you have the network of silicon atoms alone. If there is no free electron, it simply means that the electrical conduction is going to be nil at T is equal to 0 Kelvin. Whereas, what has been done here, by adding the phosphorus atom, pentavalent phosphorus atom into this, one of the silicon atom get replaced by this phosphorus atom, and out of the 5 valence electron possessed by this phosphorus atom, 4 valence electrons are involved in the covalent bond formation and 1 free electron is now introduced into the system as the free electron. Okay. And in case if you are going to add large number of phosphorus atom into the silicon atom, that is intrinsic semiconductor, then obviously it is going to result in the introduction of large number of free electron into the system. So, what concentration is being increased now? The concentration of the free electron is getting drastically increased by the addition of the impurity atoms. Right? Fine. Now, as I mentioned, this impurity atom is called as donor impurity atom. What's the reason? Because this phosphorus impurity atom, after adding into the intrinsic semiconductors, it is donating the free electron into the system, or it is giving free electron into the system, and that's the reason why the impurity atom is now called as the donor impurity atom. Okay. Now, let's focus on the energy level diagram. As I was repeatedly mentioning, at T is equal to 0 Kelvin, what will be the energy level diagram for an N-type semiconductor? Now, let me draw that first. Okay. When the system is in its intrinsic form, then obviously all the electrons will be available in the valence band. Okay. And the conduction band is going to be completely empty. Now, what we have added into the system? We have added the phosphorus atom. Once you add the phosphorus atom, what is newly getting introduced into the system? Valence electron donated by the phosphorus atom will be acting as the free electron, and all those free electrons which are donated by this phosphorus impurity atom will be lying in a new energy level, which we are going to call it as donor energy level, and I am going to represent that as ED. Okay. So all those electrons which are involved in the covalent bond formation, they are present in the valence band, and all those free electrons which are newly introduced into the system because of the addition of the pentavalent impurity atom, they all will be lying in the donor energy level. Okay. So this is the structure of energy level diagram at T is equal to 0 Kelvin for a N-type semiconductor. And you could clearly see that there is no presence of free electron in the conduction band. When there is no presence of electron in the conduction band, obviously the system is not going to act as a conducting material. Now, what happens when we are going to increase the temperature? When I am going to increase the temperature, that is T is greater than 0 Kelvin, then immediately the next consequence is the free electrons which are donated by the phosphorus atom, that is pentavalent impurity atom, will first gain energy and they will move to the conduction band. Okay. Instead of the electron moving from valence band to conduction band, as in the case of intrinsic semiconductor, now what is happening? Once you start to increase the temperature, initially the free electron introduced by the pentavalent impurity atom which are residing at the donor energy level, they will first gain energy and they will make the transition to the conduction band. And once an electron moves to the conduction band from the donor energy level ED, correspondingly a positively ionized donor atom is introduced in the donor energy level. Why? A electron is leaving out. Or if an electron is leaving out, it simply means that the atom is becoming more positively charged. When you have an atom which is more positively charged, you can claim it to be a positive ion. So, if another electron gain energy and if it is moving to the conduction band, then you have the introduction of the positively ionized donor atom. If another electron moves from donor energy level to conduction band, and another positively ionized donor atom is created in the donor energy level. If another electron moves to the conduction band, and another positively ionized donor atom is present in the donor energy level. Okay. And if I am going to take the number of or concentration of the positively ionized donor atom at the donor energy level as Nd, and as we know, the concentration of free electron in the conduction band as small n, then at the lower temperature we can claim that small n is equal to Nd. Why? If at all at the lower temperature, if an electron is present in the conduction band, from what energy level it will be coming? It has to come from the donor energy level, and it won't be an electron from the valence band. Why? If an electron need to make the transition from valence band to conduction band, its energy need to be much higher, whereas lower temperature will be only providing the smaller energy. With that smaller energy, only those electrons in the donor energy level alone can gain energy and move to the conduction band, and that's why we claim that at the lower temperature, the concentration of free electron in the conduction band will be equal to the concentration of positively ionized donor atom at the donor energy level. Now, what happens when the value of temperature is too high? When the value of temperature is too high, we cannot claim this equation. Why? Because when the value of temperature is too high, then all those electrons in the valence band will also gain energy and they will also move to the conduction band. Okay. And obviously, if an electron start to move from valence band to conduction band, what is created in the valence band? Holes are created in the valence band. So, there are two kind of transitions that are possible in case of the N-type semiconductor. Under what condition? When T is greater than 0 Kelvin. First thing, the electron can move from donor energy level to conduction band, which is actually the extrinsic behavior. And next comes the transition of electron from the valence band to conduction band, which we call it to be an intrinsic behavior. So first extrinsic behavior will be happening, followed by the intrinsic behavior, which could happen at the much higher temperature. So this is how a n-type semiconductor will behave at T is equal to 0 Kelvin and T greater than 0 Kelvin. So with this, now let's start discussing on the second type of extrinsic semiconductor, which is p-type semiconductor. So as I mentioned, now we are going to consider the discussion on p-type semiconductor. So it is also again an extrinsic semiconductor which is formed by introducing impurity atom into the intrinsic semiconductor. And here in this case, we are going to add the trivalent impurity atom into the intrinsic semiconductors. When you say trivalent impurity atoms like boron, okay, they are having the 3 valence electrons, and when you add this trivalent impurity atom into the already existing intrinsic semiconductor, then it will be resulting in the formation of the p-type semiconductors. So we have already mentioned the reason of why we are adding the impurity atom into intrinsic semiconductor. The reason is to increase the concentration of the charge carriers. Now in this case particularly, by adding the trivalent impurity atom, we have an increase in the hole concentration. Since we have the increase in the positive holes because of the addition of impurity atom, this type of semiconductors are referred as p-type semiconductors. And those trivalent impurity atom which we add into the intrinsic semiconductors, in this case, are referred as acceptor impurity atoms. Acceptor impurity atoms. And the new energy level which gets introduced is called as the acceptor energy level. We call it as the acceptor energy level. Okay. Now let's discuss what happened at T is equal to 0 Kelvin and T greater than 0 Kelvin for the p-type semiconductors. And there's a reason behind why we call the impurity atoms as acceptor impurity atom, and the new energy level that is getting introduced as acceptor energy level. Let's explore all these details from the in the coming session. Okay. Now let's see how a p-type semiconductor will be behaving at T is equal to 0 Kelvin and T greater than 0 Kelvin. Before that, what is actually happening because of the addition of the impurity atom? So for that, let's again start from the basic network that we observe in the intrinsic semiconductor. We have the network of silicon atom with 4 valence electron, which are all involved in the covalent bond formation, right? So this is the basic intrinsic semiconductor. Now what we are going to add into it, we will be adding the trivalent impurity atom like boron. So as we mentioned, this will be having the 3 valence electron. And once you add the boron impurity atom into the intrinsic semiconductor, one of the silicon atom will get replaced by this boron atom. So one of the parent silicon atom is getting replaced by the boron atom, and out of the 3 valence electron belonging to this boron atom, they will be involved in the formation of covalent bond with the 3 neighboring silicon atom. But you could see that from this silicon atom, 1 electron is being offered, but whereas there is no free electron that is available for the covalent bond formation over here, which means we have a introduction of a hole in this place. Okay. Now, due to the addition of this boron impurity atom, what has been newly introduced into the system? A hole has been newly introduced into the system. Initially, this hole was not there. Intrinsic semiconductor, in its intrinsic semiconductor form, there is no presence of hole, whereas After adding the boron atom into the intrinsic semiconductor, we could see that the introduction of hole is happening. As you increase the concentration of boron atom which is introduced into the system, then obviously it is going to result in the drastic increase in the value of the hole. Since the positive holes are increasing, we could say that this impurity atoms is leading to the formation of the p-type semiconductors. Now coming to the name, what's the name by which we refer this impurity atom? We refer it as acceptor impurity atom. Now why we call it as acceptor? Because holes are the site which actually ready for accepting an negative electron. On that sense, the holes which are introduced, they will be referred as acceptor site. So by the addition of boron atom, we are actually introducing the acceptor site into the system. On that sense, the impurity atoms are referred as acceptor impurity atoms. Right. Now let's see how the energy level diagram will look like first at T is equal to 0 Kelvin and later at T greater than 0 Kelvin. Okay. So first let's start discussing from at T is equal to 0 Kelvin. Fine. So as we have been mentioning, a simple p-type semiconductor will be having the presence of valence electron in the valence band, which are involved in the covalent bond formation, right? And you also have the conduction band, which is ready for the electron occupancy. And as you introduce the boron atom into the system, what is newly introduced to the system? Acceptor sites are newly introduced, and those acceptor sites, or in other words, those holes, will be residing at a new energy level called the acceptor energy level, that we refer it as EE. Okay, and these circles are representing the acceptor sites which are introduced by the addition of the trivalent boron atoms. Okay, right. Now when T is equal to 0 Kelvin, this is the scenario. You won't find the presence of any electron in the conduction band, and thereby the material is not behaving in its conducting state. While you also have the presence of valence electron in the valence band, completely encased in the formation of covalent bond, and you also have the presence of acceptor site at the acceptor energy level because of the addition of the trivalent impurity atom. Fine. Now what happened when you increase the temperature? When T is greater than 0 Kelvin, what will happen to this p-type semiconductor? Now when you increase the temperature value, which means T greater than 0 Kelvin, then the electrons in the valence band will now gain energy and they will go and occupy this acceptor site which are available for the electron occupancy. As we clearly mentioned, because of the addition of the trivalent impurity atom, new acceptor sites have been introduced to the system, and these acceptor sites, once we start to increase the value of temperature, the electrons, valence electron from the valence band will move and occupy the acceptor site. And once an electron occupies the acceptor site, it is gaining an electron, and thereby it will be becoming negatively ionized acceptor atom. Okay, if another electron from the valence band is making the transition and occupy the acceptor site in the acceptor energy level, then you have the creation of another negatively ionized acceptor atom. If another electron is making the transition to the acceptor energy level and occupy an acceptor energy level site, acceptor site, then you have the creation of the negatively ionized acceptor site correspondingly. Okay, so at the lower temperature, the electrons from the valence band will only be able to move to the acceptor site, and when they move to acceptor site and occupy the acceptor site, correspondingly the negatively ionized acceptor atoms are being created in the acceptor energy level. Okay, So if you say, and one thing we must note down here, once an electron moves from the valence band to conduction band, that is valence band to acceptor site, what is created on the valence band? A hole is created on the valence band. Similarly, if another electron leaves and occupy the acceptor site, and another hole is created over here, and another hole over here, and another hole over here, right? So when temperature is lower, at the lower temperature, electron from the valence band will move and occupy the acceptor sites at the acceptor energy level, and thereby you have the creation of holes in the valence band, and correspondingly you have the creation of the negatively ionized acceptor atoms at the acceptor energy level. Okay, and if I am going to take P as the concentration of holes in the valence band, and if I am going to take the concentration of negatively ionized acceptor site at the acceptor energy level as small Na, then you could claim that P is equal to Na. Okay, under what basis you can claim P is equal to Na? Because at the lower temperature we can be very sure that if at all an electron has occupied the acceptor site at the acceptor energy level, that electron has to come from where? That electron has to come from the valence band, right? If an electron comes from valence band, what is created at the valence band? A hole will be created at the valence band. So at the lower temperature, we can be very sure that the number of negatively ionized acceptor atoms in the acceptor energy level will be exactly equal to the number of holes that is present in the valence band. But what about the higher temperature? If you take very high temperature, then eventually what happens is the electron from the valence band will now gain more energy and they could move to the conduction band now. Once they move to the conduction band, correspondingly what is created in the valence band? Hole is created in the valence band. So as long as the temperature value is very higher, electron will now move from valence band to conduction band also, and thereby you cannot claim that P is equal to Na, because the number of holes in the valence band at the higher temperature will not be equal to negatively ionized acceptor atom at the acceptor energy level. Why? Because some of the electron has also gone from valence band to the conduction band, which has led to the creation of the hole in the valence band. Okay, so as we summarize this, what happened at the lower temperature? Electrons are making the propagation from or movement from valence band to acceptor energy level, and we call this to be the extrinsic behavior. Okay, and at the higher temperature, what is happening? Electron is moving from the valence band to conduction band, and we call this as the intrinsic behavior. We call this as the intrinsic behavior. Extrinsic behavior and then intrinsic behavior. Okay, so this is how a p-type semiconductor will be behaving at T is equal to 0 Kelvin, and later when you are going to increase the temperature, initially the extrinsic behavior of the movement of electron from valence band to acceptor energy level will be happening, whereas at the higher temperature the transition of electron from the valence band to conduction band will be happening. Right. So having discussed how the n-type and p-type semiconductor will be behaving at T is equal to 0 Kelvin and T greater than 0 Kelvin, we could do a derivation process and we can arrive at the expression for the density of electrons in the conduction band of a n-type semiconductor, and similarly we can derive an expression for density of holes in the valence band of a p-type semiconductors, and that we are going to do in the coming sessions. Okay, and before ending the session, let us have a small idea about the Fermi energy of n-type semiconductor, p-type semiconductor, as well as the intrinsic semiconductor. And first, let's take the intrinsic semiconductor. We have discussed about in detail. Now, if you take the intrinsic semiconductor, we clearly know that only two energy bands are involved. One is valence band and the other one is conduction band. And when T is equal to 0 Kelvin, we could see that the value of the Fermi energy, which is usually referred as EF. Okay, we are going to discuss how the Fermi energy value will be lying for the intrinsic semiconductor, N-type semiconductor, and then P-type semiconductor. Usually it is represented by the symbol EF. Okay, and if you take the intrinsic semiconductor at T is equal to 0 Kelvin, the value of Fermi energy level will be lying exactly at the midpoint between the valence band and conduction band in case of the intrinsic semiconductor. And it is also observed that as we increase the value of temperature, then the value of Fermi energy will also increase for the intrinsic semiconductor, right? And if you take a P-type semiconductor, if you focus on the N-type semiconductor, then you could see that you have three energy levels involved. One is the valence band and the other one is the conduction band. And due to the addition of pentavalent impurity atom, we also have the introduction of the donor energy level, which we refer it as ED, which is present slightly below the conduction band. This we have discussed while we discussed about the N-type semiconductor. Now, at T is equal to 0 Kelvin, it has been observed that the value of Fermi energy of this N-type semiconductor will exactly lie in the midpoint between the conduction band and the donor energy level. Okay. So, what will be the corresponding expression? EF is equal to EC plus EV by 2. That will be giving as the midpoint between the conduction band and valence band. And in case of N-type semiconductor, EF is equal to EC plus ED by 2 at T is equal to 0 Kelvin. Okay. And it is also observed that when you increase the temperature, the value of Fermi energy will start to slightly decrease. And at the higher temperature, the value of Fermi energy will be coinciding with the Fermi energy corresponding to the intrinsic semiconductor. This is in case of the N-type semiconductor. Now, let us discuss about the P-type semiconductor. Okay. So, if we take the P-type semiconductor, then what are the energy levels involved? The energy levels involved are, one is conduction band and the other one is valence band. And due to the introduction of the trivalent impurity atom, we have the introduction of the acceptor energy level EA, which is lying slightly above the valence band. Okay. Now, at T is equal to 0 Kelvin, we could see that the value of Fermi energy for the P-type semiconductor will be lying at the midpoint between the acceptor energy level and valence band. So, EA plus EV by 2. So, which means the value of Fermi energy will be lying somewhere over here. And as you increase the value of temperature, so when you increase the value of temperature, it has been observed that the Fermi energy value in case of the P-type semiconductor will start to increase, and at higher temperature it will be coinciding with the Fermi energy value corresponding to the intrinsic behavior. So, this is how the Fermi energy value will be behaving at T is equal to 0 Kelvin and also at the temperature greater than the 0 Kelvin. So, in this session, we have discussed about the N-type and P-type semiconductor, what they are basically, how they are formed, and also we discussed about how the N-type and P-type semiconductor will be behaving at T is equal to 0 Kelvin and also T greater than 0 Kelvin. Thank you all for listening. Thank you so much.